So let us now talk about Seifert-Van Kampen theorem. This is analog of Meyer-White-Torus in homology. So let us see this more through diagrams. So you start with topological spaces U and V. You consider their intersection. So U intersection V is naturally contained in U, and it is also naturally contained within V. And these are again naturally contained in U union V. So this is also contained here. And you also have this natural injective map of U intersection V into U union V. So this you can write as some space X. So this space X is covered by these open sets U and V, and you have these set of natural inclusion maps. So these are topological spaces. So now you apply this functor pi1 to it, that is fundamental group, and you land up in groups. So when you land up in groups, this entire diagram is preserved. So you have fundamental group of U intersection V. There is a homomorphism like this to pi1u, which corresponds to this map. It comes here. Let us say this is I1. And then you have homomorphism here to pi1 of V. This is corresponding to this. This you called as I2. And then you have corresponding to these two maps, you have the map here. Then you also have this map here corresponding to this. So the first thing is that this diagram is preserved. So you apply the functor pi1 to it. Second thing is that this group is universal in the sense that says there is another group H here and you have a map like this. Then you have a unique map from pi1x to H. Similarly, if you have map from pi1v to this group H, then you also have a map from here. So this is essentially what is the Van Kampen theorem. So another point we have to keep in mind is, say suppose there is an element G here. So this element G will get mapped to I1G here, and it will get mapped to I2G here. Yeah, via this I2, take it to I2G, I1 will take it to I1G. Now we obviously have to have these two equal in this fundamental group, because you also have this arrow coming in. So what was same in U intersection V should also be same in the fundamental group. So for that you have to do amalgamation. So let us write this down. Instead of X, now I will again write U union V. This will be equal to pi1u free product with pi1v, and you modulo it with some normal subgroup. This normal subgroup is essentially generated by this pi1u intersection V. So what is it? This normal subgroup is, this is generated by words like this: I1g and I2g. I1g equals to I2g. So because some g will get mapped here to I1g and then I2g here, so you have this equality here, and generally this is written as like this: I1g times I2g inverse is equal to identity. So you make sure that if something comes like this in your words, you set it equal to identity, and this is a normal subgroup. So this is equal to pi1 of x, and this is precisely what we call amalgamated product. So this is it. So let us go through the statement. So let U intersection V be open and pathwise connected sets, and X is covered by these two sets U and V. You have a common base point x0 which lies in U intersection V. Then we have a canonical isomorphism. Pi1x is equal to pi1u. There's an amalgamation here. This is amalgamation pi1v. So this amalgamation it's nothing but pi1u star pi1v modulo n, where n is generated by elements like this. So this is precisely what amalgamation means. So this we will see this in action in a bit. So let us mention two important corollaries. So if U intersection V is simply connected and non-empty, then you have pi1x is equal to pi1u star pi1v. So if u intersection v is simply connected, then obviously that means this is nothing but the identity. So this becomes identity, and then you do not require this here. So this becomes identity. So this becomes identity. So you just have pi1u star pi1v. So you get rid of this amalgamation. The corollary 2 is if v is simply connected. Now in some cases this v would be simply connected. So this fundamental group would be just the identity. So this element here will just become the identity. So if this becomes the identity, this becomes the identity. So in this case, this pi1v becomes identity because v is simply connected. Then you still have this n left, and in this case the n, the normal subgroup of pi1u, because now this will become pi1u by n. Then this n is generated by the image of pi1u intersection v. So you no longer have the amalgamation because there are no elements in pi1v. This I2g is getting mapped to identity. You still, so obviously if I2g is getting mapped to identity, the only elements remaining are I1g. So this normal subgroup is completely generated by the elements in the intersection. So completely generated by the elements in the intersection, pi1u intersection v. So image of these elements. So completely generated by I1 of g. So normal subgroup is completely generated by I1 of g. That is it for Seifert-Van Kampen theorem, and let us now do some examples to further understand the applications of each of these three results. So result 1 is this, result 2 is corollary 1, and result 3 is corollary 2. So we start with result 1. So let us compute the fundamental group of two-hold torus. So first you just have this diagram for Seifert-Van Kampen theorem. So you have topological spaces here and you have groups here. So let us first draw the two-hold torus. And let us take this as the intersection. So this is u, this is v, and this is u intersection v. So u intersection v is nothing but a circle S1. So this u intersection v is S1. So immediately you have pi1 of u intersection v is integers. So this is integers right here. So let us open this up. So the set u looks like this. So you have, say, side A here, and then say B goes from here, and then B goes from here. And this part here is this circle. So now we are focusing on u. So this circle, you are going, say, in this direction. You're traveling like this. So you're traveling like this. That means you're going like this. So you first travel. A is in the direction of our arrow. So you go A. B is also the direction of our arrow. Then this A is opposite to our direction. So you have A inverse. And this B is also opposite to our direction of arrow. So this becomes B inverse. So you're dealt with U. Now let us deal with B. So this is V. Again we will draw our circle. So this is our circle. So let sides be C and D here. So to preserve orientations, you will have D will be like this, and say C will be like this. So again, if you want to move in the same direction like this, that is, you want to move along the circle like this, same as before, like this is the same as before. You have D in your right direction, then you have C the same direction. Now D is in the opposite direction, so D inverse, and now C is in the opposite direction, so C inverse. So So this is the circle. So this U intersection V is this circle in purple. So say this circle is being traversed and we have this arrow here, so in some direction. So let us give it this direction is what we have opened up. So this is traveling and this is generated by R. So this R gets into U. So this R travel gets into U as AB, A inverse, B inverse. So this gets in here as AB, A inverse, B inverse. And this R gets in here as DC, D inverse, C inverse. Now by this amalgamation we mean is that these two have to be equal to each other. So we need to have AB, A inverse, B inverse equal to DC, D inverse, C inverse. Now obviously this you can rewrite as CD, C inverse, D inverse and taking inverse of it. So now everything is easy. This is nothing but a commutator subgroup of AB, and this is nothing but commutator subgroup of CD with the inverse. Or you have AB, CD is identity. So what is this pi 1x? So this pi 1x, you use our theorem right here. This is equal to pi 1u amalgamation with our intersection, which we have just written here. This is our amalgamation with pi 1v. So what does this look like? This will look like this. You have A, B, C, D. So we have already computed for the torus. We know for the torus this pi 1 of u, for the torus this pi 1 of u is nothing but AB, and then you have your commutator subgroup AB is identity. And similarly here pi 1 of v is nothing but CD with CD as the identity. So this we have computed before using universal covering space. So now you're going to copy both of them here. So pi 1u is AB, you get AB here. This pi 1v is CD, you get CD here. And now you use the amalgamation. So amalgamation is AB, CD is the identity. So this is our fundamental group of two-hole torus. So for two-hole torus you write it as say M2. So now you can continue doing this, adding more and more holes to it. So for three-hole torus you already know the fundamental group of two-hole torus. Now you make a new circle, you get your intersection right here, and you keep adding. Following the same procedure you will get say pi 1 of mg. This would be, so will be a1 b1 for say first torus is generated by a1 b1. The second torus, this hole is generated by a2 b2. Third hole is generated by a3 b3. So you just write this down. So instead of ab I'm writing a1 b1. Instead of CD we write it A2 B2, then A3 B3, all the way to say if there are G holes you have AG BG, and all this with these commutator groups. You have A1 B1, then you have A2 B2, all the way to AG BG. This is equal to the identity. So you can get a fundamental group of G hole torus. So we have just used the amalgamation here and this result to compute the fundamental group of two hole torus and a G hole torus.